Hello everyone, we're Team 6, and we present to you the Reverse Coffee Maker. This is our engineering-based museum exhibit designed for middle and high school students. Our theme of the Grand Challenge is providing access to clean drinking water. Throughout the semester, we acted as real engineers, identifying a need, creating an engaging, educational, and automated exhibit that demonstrates how engineering solves real-world water issues. When we think about clean water, most of us imagine turning on a faucet without a second thought, but for millions of people around the world, that simple action is impossible. Every day, children walk miles just to collect water that isn't even safe to drink. Families suffer from preventable diseases simply because they don't have access to something as basic as clean water. This reality is why we chose the Grand Challenge of providing access to safe drinking water. We wanted our exhibit to do more than just teach a science concept. We want to show young people that engineering can save lives by giving them a hands-on way to see contained water transform into cleaner water. We hope to inspire them to believe that they can be the engineers who changed this story. Our design problem was to build an exhibit that is engaging, hands-on, easy to learn, and equips them with that engineering mindset to solve problems.
The potential customers for our project are the museums in the greater Charlotte area. Our goal is to propose this exhibit and get it into the museums in order to teach kids aged around 6 to 18 with a focus on younger kids to inspire passion for engineering.
Hey everyone, I'm Mike. I'm here to talk to you about the general specs and the performance specs. Our exhibit meets all required general specifications by staying within that $150 budget, using an Arduino, including an automated feature and remaining safe, interactive, and visually appealing for young learners. We tied our design directly to the Grand Challenge of providing access to clean drinking water by allowing kids to build their own filter and test it. Meet the performance specifications. The Arduino accurately reads the turbidity levels, and the LEDs clearly show whether their filter is working or not. Red when their filter fails and they need to try again, or green when their filter has success. Altogether, these features make the exhibits hands-on, affordable, safe, and effective at teaching the engineering mindset.
Hi, I'm Chris, lead designer for our project. Our project tackles water scarcity, and its most unique feature is the interactive filter cartridges. Guests from a K-12 audience can design their own filters with sand, gravel, and charcoal and then test them. Unlike other systems, ours is fully automated and uses turbidity sensors to read water clarity, automatically pumping water until full, then empties and rinses the chamber after each test. We pivoted from this earlier design with a manual funnel to our current automated system. This adds value by encouraging thoughtful engagement from students, which connects directly to our theme of bringing access of clean drinking water by inspiring the next generation to enter these fields. For the build, we 3D printed components and used Arduinos, as you can see here.
Hello, my name is Jean-Paul, also known as GP, and as you can see, I am the lead coder of the Arduino implementation within our water filtration design. My job is to automate the water pump, which is powered by the inland relay, program the servo motors that you will see the water flow through and in and out of the testing chambers, as well as enabling the rinsing pump to clean out the testing chambers after tests are finished. I am also in charge of making sure all of the lights and buttons within our design work and making sure all the processes run smoothly alongside each other.
Our testing phase was critical, where we turned our design into a proven, reliable system. Our biggest challenge was the automated dirt feeding system. In earlier tests, this mechanism shown here consistently jammed. This was a critical feature that would have stopped the entire user experience. So, we made a critical pivot. Instead of over-engineering a complex feeder, we designed around the problem by removing its function entirely. We refocused on the user manually adding their own filter medium and dirtying the water, which allowed us to move on to testing the automation. Component tests, like that for the turbidity sensor, often failed at first, but led to successful calibrations. We then verified the full pump and rinse cycle, confirming the system could automatically fill the chamber for testing, then drain and rinse itself completely, ready for the next guest. Finally, for implementation in an exhibit, we needed 100% reliability. We ran extensive servo motor testing, cycling the main drain valve hundreds of times. We confirmed it was 100% repeatable and robust enough for continuous public use. This iterative process of testing, failing, and redesigning was essential for creating our final, reliable, and automated solution.
Hello, I'm Devin, and I was in charge of budgets and materials cost for our project. The final cost of our design was $120.27, with $99.10 coming from new materials and $21.17 coming from secondhand materials. Throughout the project, I kept a track of the budget on a sheet to make sure that we achieved under the goal of $150.
Throughout this project, we learned how important teamwork and communication are in the engineering process. We discovered that failure isn't a setback, but it's a key part of designing, testing, and improving. We also learned that our first idea is really our best one, and that iteration is essential to finding a solution that truly works. If we were to redo this project, the biggest improvement would be managing our time more effectively. Starting certain tasks earlier would have reduced stress and given us more room to refine our design. Overall, these lessons helped us grow not just as students, but as future engineers.
In conclusion, our automated interactive filter exhibit is a proven success. Our testing confirmed 100% reliability in its mechanics, and the system is now a fully functional, engaging tool ready for its K-12 audience. Our implementation plan is to deploy this in a pilot program at a local science center. From there, we will gather student feedback to refine the experience and begin designing new, more advanced filter modules.